So here is a real-world experiment dealing with relativity. On page 51, evidence supporting Einstein's theory of special relativity is found in the analysis of the behavior of muons. Muons are subatomic particles that are created in the Earth's upper atmosphere when cosmic rays, typically protons, collide with the nuclei of air molecules. Muons have a velocity of 0.998 c and a lifespan of 2.2 times 10 to the negative 6 seconds at rest, so roughly 2.2 millionths of a second, after which they degenerate into other particles. So yeah, they live about 2.2 seconds and then they go poof and they disintegrate. Now, scientists conducted an experiment in which they detected the presence of muons on the top of Mount Washington, New Hampshire. They put together kind of like a Geiger counter sort of thing, and they went to the top of Mount Washington, which is roughly 2,000 meters above sea level, and turned it on and tick, 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 tick. Yep, they were muons. Okay, so then they shut everything down and they went down to sea level. They went to one of the beaches in Maine, I do believe, but don't hold me to that. Now, even if you're traveling at 0.998 c, I mean, that's almost the speed of light. If all you got is 2.2 millionths of a second to go from point A to point B, you're not going to cover much more than 600 meters. In fact, it comes out to 658.68 meters. That's as far as you go traveling at that speed, if that's all the time you got, without taking into account the effects of relativity. Anyway, they went to sea level and turned on the detectors, and they shouldn't have gotten any muons. They should have all disintegrated by the time they got down to sea level. Turned on the detector, and tick, 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 there were muons. Well, how did that happen? What changed here? Well, if you take into account the effects of relativity, it makes perfect sense that they were able to pick up muons. Here's why. Well, we have something that's moving at 0.998 c. Let's try this one. Okay, that's certainly a relativistic velocity, so the first thing we're going to do is calculate gamma for that velocity. Gamma is going to equal square root of 1 minus 0.998 c squared over c squared. And that simplifies to 0.998 squared. And I get 0.996. And I get 0.063. All right, so there's gamma for any object moving at that velocity. So first, let's take a look at time. T delta equals T over gamma. Remember, T is time is experienced by the moving object. So that muon is going to experience 2.2 millionths of a second of life. 2.2 divided by 0.063, 34.921. All right. So, from the perspective of the observers, that muon, by virtue of its velocity, is not lasting 2.2 millionths of a second. It's lasting almost 35 millionths of a second. Roughly 15 times its normal lifespan. So yeah, that's plenty of time to cover 2,000 meters of distance. But what about from the perspective of the muon? He is going to experience 2.2 millionths of a second of life. How's he going to cover 2,000 meters in that time span? Well, the answer goes this way. That muon can make the case, can make the argument that he is the stationary object, the stationary observer, and that the Earth is moving toward him at 0.998 C. That gets us to this. Length delta, contracted length, equals original length times gamma, which in this case is 2,000 meters, times 0.063. So far as that muon is concerned, Mount Washington is a mere 126 meters tall. So from our perspective, Mount Washington looks like this, but from the muon's perspective, it looks like this. And yes, he can certainly cover 126 meters in 2.2 millionths of a second with plenty of time left over. Pretty wild, huh? All right. We'll pause here and I'll go through a few more examples.